This Hangout on Air is live. All right. This is Coder Consortium July. Thank you all for coming. Corey Minter on parser combinators. I don't know if you can switch, if you can sign into the Hangouts, but if you can, then you can actually share your screen.
So do I do it?
Or I can share your screen or something.
Do I do it separately and then?
It would be plus google.com. I don't know. How does it work?
There's only focus, not size.
Okay, hold on. I'm inviting developers. I will invite Corey, even though I'm 99.9% sure you're in my developers group. How's that? Get an invitation? Go look for your invites.
I invite where?
Maybe under notifications. Maybe try just refreshing the page. Okay, it looks like we got at least one person signed in. Haha. There you go. Awesome. Sorry, guys. My lack of Google Hangout on air knowledge.
So if I,
Corey, if you want to make that.
so if I,
It doesn't have to be like right next to you.
so will it see that I switch my screen and?
Yeah, go ahead and hit join there down below. And then I think I can see your screen. I think I can just switch you. So I've now, actually no, it's your camera. Actually,
so if I click on screen share?
Yeah, screen share over there on the left. Give the full screen a try. Let's do that. And I believe if I switch over there.
Is that working?
Yeah, it's working.
Cool. All right. So yeah, I'm going to talk about parser combinators in Scala and.
You might want to mute here. If anyone signed into Hangouts, go to mute here.
Better? Yeah, so basically, it's a funny name, but it's just how a different way to create parsers, different style than maybe some of the more older traditional parsing styles. But it's actually pretty straightforward, and people like to use them. You'll see why. The reason why the focus here is on Scala is because Scala is a functional language where it makes it easy to do this in Scala, and some of the other features you'll see why it also makes it pretty convenient to do this. So basically I'm going to talk about how Scala does it. It basically provides, gives you a library. It's not some sort of special built-in thing of the language. It comes through a library, and it's because the language has a way of sort of doing. It can make methods appear as like infix operators, which makes it convenient to do things, to create domain-specific languages, DSLs, and the other thing is it's different from other parsers, or maybe if I talk about parser generators, because what you'll actually see you doing is you'll actually build the parser inside of the language as opposed to being a separate step, which a lot of times it is. So, so I'll talk a little bit about the parsing background, but I won't talk a lot about other ways of parsing, just in case people want to. I'll mention things, but if you want to, you can go look at other tools that are available. If Brian was here, he would talk about Antler, so, which is also pretty cool. Yeah. Yep. Yeah. So then, and I'll do show you guys the code, some code behind it, and because it's in Scala, it takes advantage of the key things in Scala that you'll see why it actually makes it actually interesting to do. So here's a little bit of background. So, like when do you even need to parse? Well, parsing happens a lot, all over the place. Most everything you do, you're parsing XML files, parsing JSON, all these things, right? And sometimes you just want to parse little phrases, maybe use regular expressions, things like that. Yeah. You could actually just skip this whole talk and just do this in Perl. But regular expressions only get you so far, because if you have some recursion, you're going to be stuck. So you're going to want like a regular parser to be able to do things like that. So what are you doing when you're parsing? You're using a grammar. You define what you want to be able to parse, and that's your grammar. And it explains the rules of how the pieces of whatever that thing is you're going to parse are built out of smaller pieces, and grammar rules. And what you want to do then is transform some data input into some, quote, parse result. So I say parse result in quotes just because you could be doing anything. If you're a compiler, you're going to take the original code, you're going to transform it into a bunch of intermediate data structures. You're going to manipulate those data structures into more data structures, and finally create whatever it is that you want to do. Like maybe if you were doing XML processing, you want to, maybe it's some configuration. So you want to parse that. That turns into some configuration, and you can refer to that configuration in other parts of your code, let's say. Or maybe you're transforming something and you're just outputting it in another form. You're just, input file, transform it, output file into something else. So you'll hear people talk about abstract syntax trees, and
especially if those people are Brian.
Yeah, and the basic idea is that if you don't do anything else, your parser can turn your code into or your input into a tree, a data structure of its own representation, which might limit. Yay, Brian did make it. So, which might remove some of the details of the input file. So, like, let's say there was white space, or there's characters that you want to throw away, but it'll keep the structure of the grammar that you asked it to parse. So, then the other term you might see is abstract semantic graph, and that's just kind of a general term of saying, hey, this is just some other form of data that you've turned this into. It's not necessarily just a raw AST. So, so what are examples of where you're going to be having a grammar, right? Of course, you've got programming languages. There's a well-defined grammar there usually, and there's maybe I shouldn't say language, but config or data. Yeah. What is the L in XML? Language? Yeah. So maybe it's for configuration or data like JSON or YAML or other things like that. Or you might have, you might have a domain-specific language. So you might be doing some kind of, I don't know, just any special problem. Or like example that comes up a lot, maybe you want to do something kind of odd, but with existing existing grammars. So let's say you want to embed, let's say you have XML, but you want to embed some kind of expressions in it, or you've got sometimes programming languages will let you embed another language inside of it as well, or so there's a couple examples. So some things containing parsers, right, that you're used to is compilers, interpreters, your software, hardware, language compilers or interpreters, any data converter, and lots of other things. If you type in expression in Excel, it parses your input, right, and turns it into something that it's going to store and be able to manipulate further. So just a little background, but also to focus on, to talk about what this talk's talking about versus just parsing in general. So like we mentioned before, you've got regular versus context-free grammars. So the regular grammar is like something you could build regular expressions with. And then you can talk about unambiguous versus ambiguous grammars. And ideally you want an unambiguous grammar if you're going to process it and do something with it. But you can still define unambiguous grammars and try to parse them if you want to. But depending on what kind of parsing technique you use, you may you may run into the limits of that, or you may just get a subset of being able to subset of what it is that input means, right? So it's like maybe English language, right? You can parse it, but you're only going to get a subset of the meaning of that language. It can mean more. So, and then there's different kinds of grammars, LL and LR, and I won't go into any of that. And except to mention that and there's also LL parsers and LR parsers, and just that what we're talking about is an LL parser, which the first L means you go from left to right, and I forget what the second L is, but it has to do with how you're doing it, the parsing. So the reason why I don't pay much attention to this, it's easy to actually kind of ignore the details and do a lot of things with parsing without getting caught up in a lot of the detailed theory. And most languages that like programming languages you want to deal with are kind of well-contained things that you can parse without thinking about it, if you're careful. I mean, one of the things you have to worry about with the parser is the recursion, and if it's left recursive, depending on the parser, you'll have to rewrite your grammar to. You could, like, it gives it a good try, but it basically Stack Overflows your parser. So, and then you can within top. So basically, in terms of parsers, we're talking about here is top-down parser, or I guess a subset of top-down parsers is recursive descent parser, and then you can categorize that into backtracking versus predictive. And I think Brian would say Antler is like predictive top-down.
K-star, they have like some K-star algorithms that look ahead.
Yeah, so you're doing look ahead. Now I'll get to talking about a little bit of the difference between this and other things in the next slide, but it can be more efficient.
It's usually a common problem with top-down is that you run into, when you Antler, I found that, well, put away from you.
Yeah.
Bottom-up ones, you usually are used kind of. Performance-wise.
Performance, right? Exactly. Yeah. So what we're going to talk about is a backtracking parser, and you'll see how that happens. And then the alternative is bottom up, and so there's a whole other category. And examples of bottom up parsers would be like your Yak and Bison, things like that. All right. So a little bit more comparing parser combinators in Scala, maybe, with parser generator style of parsing. So I mentioned the parser type. This is top down versus bottom up. Like Brian was mentioning, the parser combinator is often has lower efficiency because of the backtracking, because it's not looking ahead and it hasn't figured out ahead of time the optimal way of looking at the tokens and figure out what to do next. It has to sort of try something. If that doesn't work, it might go down some path, come back, try something else. And it's part of why it's easier to kind of just see how you'll see in the code. You can see how it works. That's just a side effect of the style of doing it. I think there's probably one thing that interests me about the parser combinator is how easy it is, I think, to combine parsers. And I was kind of mentioning that if you want to create some sort of hybrid thing, you want to have one language, and then if you include some other type of grammar inside of that, it's pretty easy to just say, okay, now when I get to this point, try to see if you can parse this thing out of it. And that can either pass or not pass, or I should say succeed or fail. And so it's kind of an interesting use of parsers, which interests me. I can't say how easy it is. I remember trying to do something a long time ago in Bison, with embedding one parser in another. It was difficult. You had to be careful how you generated it and how you called one from the other. I don't know if people have experience with that. So, and what's another thing that's interesting, and this kind of the next point ties together with the grammar and action in being embedded inside the code, is that you can kind of do things dynamically if you really wanted to, and you can construct it differently. The flow of how you write code and reuse code is a lot different. I think it's nicer that way for certain things. And yeah, so then the difference is there's no extra generated code. You just compile your code, your grammar is inside of it, your actions are inside of it, and your whole program is just one unit. And just to say, both kinds of parsing have been around for a long enough time that it's pretty stable and mature technology. And yeah, and one other thing I want to mention about the performance, the way around that has to do with where one way around it is by basically this thing called pack-rat parsing. And the idea is that if you backtrack, it's not that you can keep yourself from backtracking, but if you go down some path, you parse a bunch of stuff, and if you've ever, and you come back, but you end up getting to that point again, down another path, if you've created some work, you can, this is kind of something I think they added in, like Groovy, memoization of method calls and stuff like that.
Right.
So, but what it really amounts to is you recognize where you were in the past, and you cache the result of what you figured out from that point. And so if you do that, you at least don't have to pay the cost of re-parsing and recreating to that point, because you can reuse things by caching. And so it's actually pretty easy it's really easy to do, to turn your parser into memoizing parser using pack-rat parsers in Scala. You basically just, I won't demonstrate it, but you just mix in another trait called pack-rat parsers, and you write your rules instead of as function definitions, you write them as vowels. And so I don't want to go into that, but it's pretty well documented, and it's interesting I'll just say it's interesting that the implementation of the trait of packrad parsers is like 3 pages long. And you just use it and it works. And it, it has all the caching code and all that, and just without changing your code.
Wow.
Past that. So
So you could theoretically, while you're performance testing, test it and
compare
in
easily.
each.
Yeah. Yep.
Which is really anytime you're doing any sort of memoization, it's a known issue that you're bringing, you're memoizing for.
That's a good point. There's a cost
because there is a cost.
Yeah.
Yeah. But it's a linear cost, and if you're getting, if you
Yep. And the other thing
once
is,
you've done it more than once, essentially, there's a benefit to it.
The other thing to mention is you can do it in parts too. I guess you don't have to do everything. You can do part of it that way and part of it the other way. And if it cached it and finds it, good. If it doesn't, then it reparse it. So you can. I think you can. To what you're saying, I think you could fine-grained kind of not do it. Or do
right.
It. Yeah. So basically, it's really easy. You write parser functions. You combine the functions, and you get a parser combinator. That's and you'll see it's pretty straightforward.
When does Kenny die?
In this program, he doesn't die, but
oh my God,
maybe I didn't. Yeah. So here's some more basics. So like we said, you basically want to turn some sort of input type of data into some parse result. So when I look at that, so Scala is strongly typed, and when you have that, you want this really takes advantage of that. People were saying maybe I kind of missed the commentary earlier about why would you do one thing over another. One of the I couldn't imagine doing parser combinators without strongly typed data structures. It would just be a nest of untestable corner cases that
sounds like
that
regular expressions.
Yeah, a little bit like regular expressions.
You got regular expressions.
Yeah. So it's at the top level. So I know how many people are familiar with Scala? Enough about. So I just want to bring up there's one, or how about Java and Java generics, right? So like you can say, at the beginning of Java, you could create a list, and you could put whatever you wanted in, whatever objects you wanted to into that list, and you could pull them back out, and you could run into type problems if you took out something you thought it was a different type than what you put into it. You just typecast it to something, and you might find out at runtime. But at some point they added, I can't remember when, they added generics, and it allowed you to say that you wanted to have, let's say, a list or a set or a map, and you only wanted to put certain type things into it. And so when you do that, then you can, at compile time, you can make sure that the rules of what you put in and what you take out are enforced, and it'll tell you if you violate that. There's other catches, but Scala has a similar thing, and the way that you do this sort of, they call it higher kind types, is the bracket around a type. So in this case, we have some parser of some type T. So you have a parser of some type T. So it operates on, at some level, somewhere down below, it operates on some thing of type T. And the whole point of what it's saying is, or the usefulness of it, is that you can talk about all the operations that you want to do on that type, and then delay what the details of that type down to certain operations that where it doesn't matter. It's not explaining this very well. I'm trying to just kind of give a high level, but basically it allows you to have behavior defined, and then the type that you want to operate over it is sort of generically defined. So in this case, we want to take some input, and we want to get to some parse result, so of some type. So, like, let's say if you were talking about the common example for parsing is like parsing some arithmetic expression, right? Plus, minus, multiply, divide, and that's like the classic example because everybody knows, you do multiply and divide before you do the addition, right? There's rules, there's precedence rules and things like that. If you have parentheses, then you do things in parentheses first and all that. So you could say the parse result at the end of parsing an arithmetic expression is would be a real number, right? So you've got all these little pieces, but at the end you just want to have some real number. So that's what the t would be in this example. So and then the input. So what is the input? So the input is like in this case, it's going to be a stream of something. So you're going to have some reader that can read. So like a file reader, string reader, whatever it is, that can basically turn some object into a stream, and the type of things that come out of it are some element. So I'm still not saying what those elements are. So the compiler is still, or the parser is still written in terms of some lower level thing. So in this case, usually that lowest level thing is probably a character. But I'm just pointing this out that it doesn't have to be. It could be, you could actually have some other thing feeding tokens in or some other thing, and you can just figure out what to do with them in this grammar that you can write. So then the result of this operation, going from input to parse result, you want to think of three things that could happen. So like imagine you're looking at a math expression on a board, and you're looking and it says 1 + 2 × 3. So you want to go along, you want to see the first thing, it's a 1. Say, okay, I've got some real number, 1. And then somewhere you're going to have a rule that's going to say, I'm going to match on 1. So, but the way the parser combinator is written, you basically have something that's going to try to match on 1. So it might be that the person, instead of 1, it said 1x or 1a or something illegal. So the way you want to think about it is each of these parsers, it could either succeed and it gets that thing that you asked it for, or it can fail, and in that case it usually means, I'll talk about what it means. And then the other thing is you can have an error. So there could be other ways of saying, I just want to say this is an error. So the success thing is pretty straightforward, but the fail is what allows you to move on and try the next thing that could be the thing that you want that might match. So and then the goal of in writing a parser using parser combinators is really just to combine parser functions and make them into a bigger grammar, and then I'll get to this later, but then you have this actions that transform it into some other thing that you want it to be. So in that first example I talked about, where you wanted to, if you're going to parse 1 + 2 × 3, you're going to parse the 1, you're going to parse the plus 2 × 3, but at the end you're combining these things, and you're combining this up to some final real number. So and then what you have then, when you combine all these things, is a combinator parser. So by the way, the only reason why I included this picture was because I forgot in the Matrix there's a lot of this shots where you can see the glasses and see what they're looking at, including there. And so, and if you guys remember this, okay, so the interesting thing is everything's a parser. Terminals are parsers. So at some level you're saying, I should back up. In a grammar, I'll show you what a terminal is and a non-terminal. But a terminal are the things that are sort of like at the bottom of the tree. So they'd be like the number that you want to recognize, the character that you want to recognize for an operator. The non-terminals are the other operations that you're saying, okay, I have this plus this. That's a sum operation, where you're combining things together. So terminals are parsers. Then you have I'm realizing I probably should have showed you one picture before I start talking about this. Are you guys familiar with JSON? Yeah, so I'm gonna show that as an example for parsing because it's kind of small and easy to show. And so let me. How do I?
And the problem is, so now you've got a difference here. Now, with true north, you've got your magnetic north, you've got a difference.
You're no longer screen sharing at the moment.
Okay.
Just so you know.
I need to.
It's okay. Take your time.
Do I guess I share per app. Is that how it works? Or should I
think
share
you
on a
did,
desktop
yeah.
or something?
You had a bunch of options.
So I'm just opening up the example.
You could go over a map someplace like a difference of 14 degrees. Say, well, I'm either in the middle of Siberia or the middle of Australia. I'm not in Japan, I'm not in the United States, you know, like you could crunch it down, find it. But if there were two places on Earth, believe me, there's a lot of them. It's the maps that show magnetic declination. It's like a contour map. There's a line like this down the map. And on that line, magnetic declination is those maps and everything. Think about it.
Are you able to screen share that?
Yeah, let me figure out how to do that. Good at that.
I'm able to switch back one view to another, so right now it's just pointed at your face.
Oh, okay. Yeah, I'm trying to figure out how to change the. I suppose if I go back to the.
Go back to the share screen.
This
Probably. Where were you?
Your compass needle will say magnetic north is over there.
Yeah.
And I say
Hey, it's up. Is it the green one? The green one with the arrow?
screen share.
Yeah.
Oh, screen share, but choose something else, right?
You do. There you go.
That one, right?
Give it a try.
Well, no, a magnetic compass will also point
I'm not seeing it.
magnetic.
Oh, unless the screen you're showing. Oh no, it's working. It's just you were pointing at
Oh, okay.
yourself.
All right.
The screen was looking at you. Was this looking at you? You looking at this, looking at you. There you go.
If they didn't, they would just fancy ways of finding either two. Instead of finding boundaries from. You have to have a plot. The Earth is spinning. It takes a plot to know how much it's spun.
Sorry, we're waiting for NetBeans to load. All right, I think you can see that, but it's probably not big enough.
Hazelcast test. Look at you.
Not big enough. How does it look on the Hangout? Well, actually, that should be easy for people to read.
Looks good.
Okay.
Yeah.
So I was the reason why I wanted to come to this. I didn't think about this before. Is that I want to talk about. It's kind of confusing, the idea of things, terminal things versus non-terminal things. So think about JSON, right? You've got like brackets, right? You've got key names.
Strings.
You've got, what's that?
Strings.
Yeah, you've got strings. You've got key names, strings as key names. You might have strings as values. You might have like a comma-separated list in an array. Then you can nest all this stuff, and and you can have numeric values. You can have true, false, and null, I guess. And so the true, the characters true, true, fal, false, anything in quotes, a number. Those are the terminals, and then the things that are ways of combining those are the non-terminals. So if I look at a JSON grammar down here, I guess kind of it's called eBNF or BNF style. What you have here these are grammar rules, and you're saying for me to have a value. So for me to have a value, it can be any one of these things. A value can be an object, an array, something in quotes, a string literal, a floating point number, or these characters, the string null, the string true, or the string false. And then you go, oh, okay, but what are some of those are familiar, right? But some of them are like object and array. What's an object? Okay, an object is, well, it starts with the left brace, some repetition of, or something that represents members inside that object, and then a closing brace. And then an array is similar. It has the brackets and square brackets and some values inside and closing brackets, right? And then, oh, okay, so then it keeps going down. So members now, what are members? Okay, a member is, or members, plural, is a member followed by an optional comma and another member. So, or I should say, and then a member itself can be a string literal, or I mean, is a string literal colon, and then some value, and then values. Similarly, the values can be comma separated list of values. So, by the way, I'm going to get to this in a second, but this is the parser. You see, that's very close to what the grammar itself already is. But I'll come back to that. Okay. So some of the things that you saw were you saw sequences of things. I have to have open parentheses, open braces, followed by some things, close braces. That's a sequential operator. If you have choices where you could have said, oh, it can either be a string or a floating point number or something else, that's an alternative. So those are the two like fundamental operators. But there's actually a bunch of other ones that you can have that I believe you can build everything on top of those too. But these other ones make it easier to kind of make it simpler to declare your grammar. But they are things like options. So an option is either none or one of something. You spell it repetition, so you can either you can have 0 or more. So I'm talking about the list on the right. So repetition is 0 or more. You can actually have rep 1, so 1 or more. You can have repetition with a separator. So that's kind of convenient. It's actually convenient to have that, because to make it from scratch is kind of a pain. You basically want the thing, comma, and more of the thing. And then these last two are kind of weird, or a little bit strange, but if you're familiar with other parser generators. You've got your grammar, and then you've got your like action code. And the inside of the way it's written in Scala, it's actually sort of kind of blurred. It's all together, because if you don't do anything, you get something back that is a valid parse result. And if you have, the way you do actions is they're actually just transforms of what you've done so far into another parse result. So, and it looks, once you realize that that's all it is, it actually makes it a lot simpler. But so there's two more things that you can do. You can take what you've parsed already, and if it was all successful, execute a function on that, transform it into something else. And there's a simpler case of that with the 3 carets at the bottom, where you're actually just giving a value. So it's not really a function of anything. It's just, if I see this thing, I want this value to come up. So sometimes that's useful for things like constants or true, false, things like that. There's really no more. And so the whole thing of that's really cool about this is that these are just all done in Scala with any function that you define, you can actually use all the kind of like special symbols. I don't know about all of them, but you can use those special symbols. You can define a function. Let's say, so in this case, the symbol for sequential composition is going to be the tilde. So you're going to see tilde a lot, and the one for alternation is the vertical bar. And those are just methods defined on a class, and they just actually have that name. So the name of the method is tilde, and then it takes can take arguments. And if it's going to be a binary operator, like A tilde B, then really what it is a function with just one parameter on that class. So what's cool about that? Oh, and the reason why, you remember the movie, he's smiling because he's just imagining the steak that he's eating and all this stuff, right? I guess he's so the cool thing is these are actually the functions that implement those operators. I mean, that's really all there is to it. They're not more complicated. They're not like some special library somewhere. I mean, they are in the library, but that's how it is. So I guess I'll kind of skip this. This first one is like defining a token. The reason why I showed it here was just to kind of show you that whenever you give some sort of quoted text, you're actually one of the features of Scala is it allows for implicit conversion if you have a conversion defined. And so in that case, it will see like a string, and it will turn it into sort of like a parser that takes that string as one of its as part of its state. So in this case, it'll give like a special parser, an element parser. And if you can imagine what it does, it's sort of just like, so when things that match on strings, they'll say, oh, if I'm trying to match, like, say a Java keyword like try or something like that, right? So try. So the thing that wants to try to match try will try to take 3 characters from your input, see if they equal try, and if they do, it succeeds. And remember earlier I said there's 2 kinds of things. You can either succeed or fail or error. So in that case, it would say success. I found this thing called this string called try, and it will whatever type you wanted it to be, it will become. If it failed, then depending on where you are in these other functions, you would hit one of these other cases. So if we were talking about the sequential, and I guess I don't know if people are interested in this or not, but I just kind of wanted to show that it's all just right here. So if you follow the rules through here, the success for some sequence of things is if I match the first thing, and that succeeds, then I'll try to match the second thing. If both of those things succeed, then I'll return a thing that combined those that succeeds. If I don't, then it'll return failure. So then, whatever called it will just return failure or success. And you combining all these things in those ways is just your grammar. So yeah, if you get a chance, I didn't. When I was first learning this stuff, I kind of glossed over these details, but I just wanted you to see it. It's actually, there's not much there. So I'll go. Yeah. So now I'll start talking more about the example grammars. So the first example I wanted to finish then is the JSON, because it's kind of a neat example.
Is there any way to make it just a little bigger?
Yeah, let me see.
I think it'll just show a little bit. I think it's actually easier to read here than it is up here.
Let's see.
Maybe just view or Control plus or something.
I don't know if that's. Let's see.
Yeah, so Shift plus. I don't know. Checking for external change. What have I done to you? That would be huge.
Is that too huge?
It might be a little.
What did we do? Yeah, we went from 13
We might go to
to
18.
18.
14 usually.
We were on 13. So
For guys like me who are fairly blind, they do 14.
if that helps.
Yeah, I think 18's pretty. Yeah, that's pretty big.
Better, right? Okay. So what's cool about this is if you just compare. The first thing to do, just like visually compare the difference between like the way you would normally, when it's normally grammars are thought of, kind of think of them this way, and you'll see it's the same thing, really, pretty much. So everything that was a bar is a bar for alternatives, and there's everything that was just next to each other has this operator in between for a sequence, and strings are quoted here, and then this rep sep means I want to repeat on this member object, and the separator is going to be a comma, and then remember how we talked about what the parse result type is. So in this case, any is sort of like it's sort of like object in Java. It's sort of like it's the super type of everything, and so what this parser is going to do is it'll parse and return just whatever each of the rules combines into. So we can run this, and let's see. Oh crap! Should. So let's go back here. I want to show you okay, so what this, now I also want to back up. So this, I define this as a trait, and it extends Java token parsers. What that means is that there's a bunch of sort of predefined things that I didn't have to define. String literal is defined in Java token parsers. Floating point number is defined there. And so is these operators. So because I'm extending this thing called Java token, I'm extending and I'm getting all those functions that we talked about, the tilde and the or and all the other functions. They're actually, I'm including those, and so I'm sort of extending that thing that already has those defined. So so this thing needs an outer sort of main, right? So this is what we're going to run, and so I won't go into more details, but this now I just have an object so it's not a class that you can instantiate multiple times. It's sort of like, think of it as a singleton of the thing, and it also has all those methods. And what I'm doing here is I'm actually just defining another method, if you like from Java, where you have a main method, and then that will let me from the outside say, oh, this class has this object has a main method, static main method, and I can call it with these arguments. So I'm just going to take the first argument, create a file reader, and pass this file reader into the parse all method, which I didn't define. It was built into that original trait for the Java token parser. And I'm not saying what to do with it. It's just going to give me something back, right? So let's go here. Oh. So I'm going to, the other thing is I'm going to run it on this. So I'm just going to have some, so this is an object, should be an object, should have two members in it, one with the key of group 1, other key group 2. That also is an object, and it has more keys and different kinds of things. There's a string, an array of strings, just a Boolean, right? A bunch of other stuff. Here's something different. There's a double or real number. Another Boolean and null. So I should be able to parse that. It should be legal. So what does it give me? Well, let's see. See, it's a bunch of stuff. It's just what it is if you don't do anything, you get these things called parse results of just some generic thing. All it does when it matches things, it sort of just kind of like combines them into bigger objects that have those things nested in them. So what you're seeing is that it did create this object, and it had all these pieces inside that that kind of show you that it. I mean, if I pulled this apart and you looked at all the parentheses, you'd see nested parentheses of each of those things in that same structure. So one thing I'm going to do now, I'm going to switch to a different example. So here's kind of like your standard example of like an arithmetic expression. So I have the grammar at the bottom here. So let's say this thing, we want to have this thing can take, well, it can see plus and minus, and it can do, it sees something plus something or something minus something. And you might notice that I have plus and minus separated from the multiply and divide, and that's that actually gives you the precedence. So what it says is, if I want to find out if I have an expression 1, first of all, I find out if I have this expression 2. Well, what is expression 2? So I have to go down here and I go, okay, do I have an expression 2? Well, expression 2 is made of expression 3s times expression 3s divided by expression 3s. Well, what's that? That could be a floating point number, or parentheses wrapped around another expression. So you can see how it's like recursive. Even the grammar is recursive in itself, but it's not fully recursive because there's a way out where you have a number, right? But with the rules defined this way, we'll have multiply and divide will be handled or grouped together before plus and minus are grouped together, and then also parentheses will be done at the highest precedence as well.
Hey, so Corey, whenever a good breaking point is.
Yeah. Okay. So let me run these two examples, and then so again, this is the same. Pretty much looks the same up here, and you can see it just translates directly. And if I run that, whoops. Oh, I switched. So I don't have different mains for everything at this point. I have a kind of a top level thing where I run it, and I give it an argument, and it branches off and does one parser instead of another. So you'll see so I'm going to do A1 and then give it this other file. So there you can see it pulled apart things, and you can see it. It said 1 plus 2 something. It's doing the multiply and so on. But you're not seeing anything useful yet. So I'll skip. I'll skip the text example, and I will show you one more. No, let's break. This will be a good break.
Okay.
Yeah.
Uh,
So then when you come back, I'll show you how to do something useful, right? All we did was like prove that we could recognize something. We haven't done anything with it. So we're going to turn it into something else.
Can you create a parser with a random number? I don't know that we have a better random number. Did we ever figure out a good random number generator? What was that? Did we have something online? What was that?
Somebody thinks.
You mind looking something up? I'm actually looking for my notes on. There we go. So let's see. I actually have. So I have a few things to give away. Let's see. I'm actually going to start with the. Actually, I'll go the opposite way. I'll start with the most difficult ones. So it's questionable, which is more or less difficult. So Manning, one of our sponsors, the way it works there is basically you can choose any Manning ebook. You give me your name, email address, and the name of the book, and I will contact our sponsor, and they'll send you the book or the link for the book or whatever. And so you get the book that way. It'll be licensed to you. So why don't we start with the Manning book as our first giveaway? Who's our random number generator? Should I look it up? Actually, I'm going to stop broadcasting for the moment because we're about to take a break.